Thanks for your introduction. Hello, everyone. This is Zhao Chenzhang from Nanjing University. Today, I'm delighted to share with you our recent work, which is focused on enabling virtual priority in data center congestion control to mitigate the shortage of physical priority queues. Firstly, let me provide some background information. Priority queues are widely used and play an important role in data center network. In general, priority queues serve two primary purposes. The first is providing traffic isolation for different traffic classes. For this usage, each traffic class uses a priority queue, with this priority queue weighted sharing the bandwidth. The second is performing traffic scaling in the same traffic class. For this usage, the traffic scaling algorithm assigns different priorities to different flows within the same traffic class, with higher priority queues is strictly prioritized. To meet the both purposes, a large number of queues are required. For the isolation purpose, the queue requirement is the number of traffic classes. For the scheduling purpose, the queue requirement is determined by the scaling algorithm, which is typically 8, and more is better. Therefore, the total queue demand is the product of the two numbers. However, only a few priority queues are offered. The number is directly limited by the priority-related protocols. For example, PFC only supports 8 priorities as the enable vector in its header is an 8-bit bitmap. DSCP, a field in the IP header, which is widely used to indicate priority, only supports 12 priority mappings as per the standard. As a result, current commercial switches typically support 8 and no more than 12 priority queues. Besides, the trend of decreasing buffer-to-bandwidth ratio in switches further limits the number of priority queues in the future. A study from Microsoft reports that they accommodated only 2 lossless priorities on Trident 2 to conserve buffer space. In contrast, the newest switch chip has only less than a half buffer-to-bandwidth ratio than Trident 2, preventing the support for additional priority queues. The growing demand of priority queues, along with the current shortage of physical priority queues, has made virtual priority an attractive solution. Virtual priority is the capability of supporting multiple strict priorities within a physical priority queue, which must achieve the following objectives. First, the virtual priority mechanism must ensure strict prioritization of higher priority traffic. Second, the virtual priority mechanism should aim to fully utilize the bandwidth without any waste. With virtual priority, the limited physical priority queues could be reserved for isolation across different traffic classes. For example, 9 physical priority queues are needed to support isolation of 3 traffic classes and 3 scaling priorities. With virtual priority, only 3 physical priority queues are needed for traffic isolation. However, existing virtual priority mechanisms primarily involve traffic scaling algorithms that operate on switches. They need either programmable switches or additional specialized hardware, making them not readily deployable. Given this situation, we raise the question, can we achieve virtual priority without switch replacement or upgrades? Our insight is that virtual priority can be achieved by carefully managing bandwidth contention among flows within a physical priority queue, which is a task traditionally handled by congestion control at the host. Therefore, the virtual priority mechanism must be tightly integrated with congestion control. We first test D2 TCP, which is the state-of-the-art data center congestion control that can prioritize a proportion of traffic by reducing their rate less significantly. The figure shows 2 D2 TCP flows with different priorities start at the same time. Shortly after the initial start of two flows, they both decelerate. Our analysis indicates that this is because when the Q length reaches the ECN threshold, ECN concurrently notifies both flows to slow down. Each time the Q length exceeds the ECN threshold, high priority flow will reduce its rate. Although this reduction is moderate, it prevents high priority traffic from occupying all the bandwidth. As a result, D2TCP violates the multi-priority assurance objective. To conclude, we find that congestion control based on the single-bit congestion signal like ECN cannot achieve virtual priority. In contrast, let us think what if congestion control uses a multi-bit congestion signal, say delay, and set higher congestion threshold for higher priorities. In this way, when flow with different priorities contending the bandwidth, high priority flows will not preserve congestion and maintain their rate, while low priority flows continuously detect congestion and decrease their rate until they relinquish all the bandwidth. In conclusion, we get our second insight. Congestion control that supports virtual priority requires a multi-bit congestion signal and setting distinct congestion thresholds for flow with different priorities. We then investigate whether Swift, the state-of-the-art delay-based data center congestion control, can achieve virtual priority by setting different target delay thresholds. We run two high-priority Swift flows at first, followed by two low-priority Swift flows, starting after 100 microseconds. The figure shows the sending rate of one flow of each priority. The low-priority flows start at the line right, causing congestion and leading to a deceleration of high-priority flows, thereby violating the multi-priority assurance objective. As the flows run, high-priority flows gradually dominate the bandwidth, while low-priority flows send at the minimal rate, equivalent to send one packet around every 80 microseconds. When the high-priority flows end, the low-priority flows experience an 80 microsecond idle before detecting the end of the bandwidth contention by the next packet's ACK. This results in a slow rate increase, thereby violating the work conservation objective. In conclusion, we had our third insight that existing congestion controls need to be helped to balance between multi-priority assurance and work conservation. Based on the above insights, we propose PowerPlus, a congestion control enhancement algorithm that can be integrated into existing delay-based congestion controls to enable virtual priority. PowerPlus key concept is delay channel, which is a specific delay range assigned to each priority. Channels with larger thresholds are assigned to higher priority. By restricting flows of a priority to accelerate in lower delay channel, controlling the delay to its delay channel, and suspending transmission in higher delay channel, PowerPlus could meet the performance requirement. Each priority has two delay thresholds, D-target and D-limit. D-target is the target delay of the congestion control to be integrated in, while D-limit defines the boundary of different channels. We gave an overview of the PowerPlus design through the workflow of two PowerPlus flows with two priorities. When both flows start, delay began to increase. Once the delay exceeds the D-target of the lower priority flow starts to reduce its rate. After the delay exceeds the D-limit of the lower priority flow, it relinquishes the bandwidth and instead uses probe to investigate the network environment. After the high priority flow finish, the low priority flow observes a delay equal to base RTT and decides to start its transmission. However, delay equal to base RTT indicates that the path's utilization may vary from being completely idle to just adequately utilized, but no queues are built up. PowerPlus employs linear start to start up in this case. After the restart of the high priority flow, the observed delay is lower than its delay channel. At this point, it is necessary to precisely increase the delay to its channel to prompt lower priority flow to relinquish the bandwidth. PowerPlus achieves this goal by using dual RTT adaptive increase. We will now introduce each part design of PowerPlus. First, let's introduce the probe. After a lower priority flow relinquishes the bandwidth, it sends minimal-sized probe packets to probe the network delay. The Strawman solution for probe is sending a probe packet once per RTT. However, it will cause two issues. The first is collision. In the presence of high priority flows, all low priority flows simultaneously start to probe and then restart transmission if probe delay is low, potentially leading to transient congestion. The second is bandwidth occupation. Although in the typical data center environment, probing once per RTT requires only 42 bps. It can also impose a heavy load when there are numerous flows. Our solution is to send a probe after delay minus the target plus a random time selected from 0 to base RTT, following relinquish the bandwidth of the previous probe's egg is received. This solution incurs lower bandwidth occupation, while higher priority could keep higher probe frequency, and it can reduce collisions. Please see our paper for the solution on probe loss. Then we introduce linear start. When facing an uncertain environment, a flow should choose the startup strategy carefully. Starting too fast may violate multi-priority assurance objective. Starting too slow may violate the work conservation objective. For this problem, modern data center congestion control solution is to start at the line rate, which could incur 1 BDP Q built up at maximum. Internet congestion control solution is to start at a low rate and accelerate exponentially. It can reduce the potential Q buildup but incurs transmission delay. Different from the existing solution, PowerPlus starts at a low rate and accelerates linearly. It incurs less transmission delay and potential Q buildup than exponential start, thus effectively balance the two objectives of virtual priority. Furthermore, we prove that linear start is the start strategy that incurs the least potential Q buildup when increasing to the line rate in the given period. The last design in PowerPlus is dual RTT adaptive increase. Due to time constraints, we omit the detailed introduction of it. Please see our paper for the design and analysis. Finally, let's explore how to configure the channel-wise of PowerPlus. The principle is to ensure that the delay variation of a priority does not exceed the channel-wise during transmission. Therefore, it must accommodate congestion control's normal fluctuations and the noise in delay measurement. PowerPlus employs unique designs to compress channel-wise as much as possible, thereby ensuring support for more priorities within an acceptable delay range. First, PowerPlus uses a delay-based flow cardinality estimation to compress the congestion control's fluctuations. When delay exceeds the limit, PowerPlus flow estimates the flow cardinality by observed delay and its own window, then adjusts its increased step size inversely proportionally. Second, PowerPlus uses a simple filter mechanism to filter out infrequent large delay noise. Please see our paper on how to determine congestion control's fluctuations and delay noise in different network environments and set channel-wise accordingly. Here we give some testbed evaluation results. We implement PowerPlus in DPDK based on a Swift implementation. We add 79 lines of code to incorporate it. The channel-wise in the experiment is 4 microseconds. We select 4 adjacent priorities from 3 to 6, each with 2 flows to evaluate PowerPlus in real implementations, as shown in the figure. Plus with Swift achieves virtual priority, while Swift itself could not. In the simulation, we first evaluate Plus in flow scaling scenario, where Plus use up to 100 microseconds delay range to support 24 virtual priorities. The results indicate that regardless of the number of supporting priorities, the performance of Plus with Swift close approaches ideal physical priority with Swift, with the average FCT being at most 8% worse. Here, the ideal physical priority is the physical priority that being free from protocol constraints and the PFC headroom occupies no switch buffer. In the co-flow scaling scenario, when the load is at 40% and 70%, the average speed up ratio of Plus with Swift is 12% and 21% higher than that of physical priority with Swift. Finally, let me make a conclusion. Plus is a congestion control enhancement algorithm that enables multiple virtual priorities within each physical queues in data centers. It is lightweight, requiring fewer than 100 lines of code modification to existing congestion control implementations. And our code is publicly available online as a contribution to research community and to ensure reproducibility. Thanks for listening.